right, this is going to be our notes video over section 4.4, just one video here. The most important part of this section is theorem 8 and then our definition of coordinates. So if you have a basis for a vector space, then there has to be an x in each part of the vector space that is a unique set of scalars or a unique set of constants times that basis that creates that linear combination. So what does that mean? So if you have a space V and you have your basis here in your set B, then for any other x in that space, it must be a unique linear combination of the vectors in the basis. Now we call those C1 to Cn's the coordinates of x. Now they have to be unique, so we call those the coordinates of x. So we take the basis, we do a linear combination that it's a unique set of scalars. Those scalars are called the coordinates of x relative to our basis. Here it says if C1 to Cn are the B coordinates of x, then the vector in Rn we can write like so. So we can just say that x is equal to these constants, and we call that the coordinate vector, okay? X to that coordinate vector is called the coordinate mapping. So let's look at a couple examples to put all of those definitions into place here. So if we're looking at a basis, two vectors in R2, and it gives us B1 and B2, and you can see that those would be linearly independent. There's no way to multiply something by B1 to get B2. And then suppose there's an x in R2 that we know the coordinate vector for x is -2, 3. Find x. Well, let's go back to our definitions here. We know that what that means, if this is the coordinate vector, right, is that C1 must be -2 and C2 must be 3. Therefore, x must be -2 times B1 plus 3 times B2. I'm given B1 and B2, so -2, 1, 0, plus 3, 1, 2. That's going to give us -2 plus 3 and 0 plus 6. So that must be the vector 1, 6. Show that the entries in that vector 1, 6 are the coordinates of x relative to the standard basis E1 and E2. So in order for us to have a standard basis, E1 and E2, we say that E1 is 1, 0, since I know I'm in R2, and E2 is 0, 1. So they're essentially the most basic or elementary pieces, so that would be our standard basis by definition. So if x is 1, 6, then that means I need to multiply 1 times 1, 0 to get 1 up in this top part, plus 6 times 0, 1 to get 6 down in this bottom part. Therefore, we can say this is 1 E1 plus 6 E2. And that's going to be the entries here, are coordinates of x relative to this standard basis. All right, let's look at another example. If we let B1, B2, X be all of those things given, and we say that B is a basis, okay, for our R2 here with B1, B2, okay, or for our space. Find the coordinate vector of X relative to B. So let's go again back to that definition. I know that X must be equal to a linear combination. Ooh, I don't know why my pen, there we go, of my two basis vectors. There, maybe that's better. All right, so I know that 4, 5 must be equal to C1 times B1 plus C2 times B2. Now, if you remember back to when we did matrix multiplication before, that means that this is the matrix 2, negative 1, 1, 1 times the column vector C1, C2. A way that we can solve this then is augmenting B1 and B2 with our X vector. So if I take negative, let's switch these two rows first. 1, 1, 5. 2, negative 1, 4. And so I know that negative 2 row 1 plus row 2 into row 2 would give me 0, negative 3, and 6. And so I end up getting that C2 must be negative 2. Did I do that right? Oh, no, this is negative 6. Sorry about that. So negative 10 plus 4 would be negative 6. So C2 must be 2. And if that's the case, then I can plug in 1C1 plus 2 has to be 5. And so C1 has to be 3. And so my coordinate vector must be equal to 3, 2. All right, a little bit more here from our textbook. So the matrix in the one we just did, okay, changes those B coordinates in the following way, so that way we can say that X must be equal to this like A vector, I guess, or P matrix, actually is a better way to say it, let's call it that, P matrix of the column vectors of your basis. And so if you notice, if we go back up to what we did here, this is essentially just saying exactly what we did right here. So this is what we call that P for your basis. This is what we're trying to find, right? We're trying to find that column vector for the basis, and this is your X. It's just on this other side. And so that just kind of gives you an understanding of what we did here. And we call that matrix, that collection of our basis vectors, column vectors, we call that the change of coordinates matrix. Now, it must be true because of invertible matrix theorem that you could find your coefficient vector for x by doing this right here. So let's look at another example. This will be our last one. Okay, use coordinate vectors to verify that the polynomials 1 plus 2t squared, 4 plus t plus 5t squared, and 3 plus 2t are linearly independent in P2. So what does that ask us to do? Let's first look at the coordinate mapping for P2. So P2, polynomials of degree 2, are always of this form: a naught plus a1t to the power of 1 plus a2t squared. So we can think about our coefficients as being these things in the front, same thing we would have had as coefficients to begin with. And so we can call that a naught, a1, a2. So let's use this to find polynomial representations in matrices of the coefficients for the three that are given. So maybe we call this P1. So those coefficients would be 1, 0, 2. P2, those coefficients would be 4, 1, and 5. And P3, those coefficients would be 3, 2, and 0. And let's put these all together in a matrix. And then a quick reminder that those three columns will be linearly independent if this times x is 0, only when I have 0 as my solutions. For the sake of time, I'm going to just let you know that the reduction of this vector, or this matrix, ends up being 1, 4, 3, 0, 0, 1, 2, 0, and then this bottom row ends up zeroing out. So because of this piece right here, x3 is free, the other vectors are going to be dependent on this. We do not get linearly independent pieces for these polynomials, so they are linearly dependent. What does that mean? So what that means is you could then write any one of these in terms of the other ones. So I could write 1 plus 2t squared in terms of a coefficient times this, or a constant times this, plus a constant times this, because they are linearly dependent pieces. Or you could choose any of them to do that.